Ice. By the millions of tons each day, ice crystals form in the atmosphere, to be deposited in ornamental etchings, to drift gently from a winter sky, to fall violently in the heat of summer. On windswept mountaintops and in frigid laboratories, scientists are probing the mysteries of atmospheric ice. Most precipitation comes from tiny ice particles, which then grow and transform in endless variety. Yet despite all we've learned from laboratory studies of ice crystallization, we still have a limited knowledge of how ice crystals grow within a cloud to produce snow, rain, or hail. These complex mechanisms are the key to a better understanding and perhaps modification of many storms. Individual molecules of water, 2 atoms of hydrogen and 1 atom of oxygen, are attracted to one another by strong electrical forces called hydrogen bonds. A few degrees above freezing, the molecules arrange themselves along the lines of the hydrogen bonds to form symmetrical pyramids or tetrahedrons. When freezing takes place, the tetrahedrons interlock in a hexagonal pattern or crystal lattice. In a single ice crystal, 10 million molecules may be lined up along one axis. But water does not always freeze at 0 degrees centigrade as we would expect. In fact, it may resist freezing all the way down to -40. To form ice, then, something is needed in addition to low temperatures. After these water drops have been supercooled to about -10 degrees, they will still be in a liquid state. But observe the supercooled drops under polarizing filters. At the touch of a foreign substance, the drops freeze instantly. What was needed for crystallization to occur was a solid nucleus, such as a speck of dust or another ice crystal. These processes occur regularly in the atmosphere, for many clouds extend above the freezing line and become supercooled even in summer. Photographs taken inside a supercooled cloud show that it contains a mixture of minute water droplets and ice crystals. The microscopic particles which cause the droplets to freeze are called ice nuclei. They may come from natural sources such as dust storms and volcanoes, or from man-made pollutants such as industrial smoke and automobile exhaust. Once nucleation takes place, an ice crystal can grow by another process called sublimation. Since water has a higher vapor pressure than ice, water tends to evaporate from the droplets and to deposit on the surface of the ice. Thus, the crystal grows at the expense of the surrounding droplets. When it becomes heavy enough, it begins to fall. Snow crystals have intrigued men for centuries, but only in recent decades have scientists begun to decipher their patterns of growth. One method of study is to collect actual snowflakes and preserve them in a sub-freezing bath of kerosene for examination under the microscope. Within the basic hexagonal structure imposed by the crystal lattice, there is an infinite variety of forms. Snow crystals can also be grown artificially, using techniques developed in the 1930s by Ukichiro Nakaya. Nakaya's and later experiments have shown that the form a snow crystal takes depends upon air temperature and vapor saturation. Once on the ground, snow takes on other significance. Its high reflectivity prevents the surrounding air from warming and thus influences atmospheric circulation patterns. Where it persists in glacial sheets, it acts as a geologic force and has long-range effects on global climate. And in many regions, the runoff from mountain snows is an indispensable source of water. One way to meet growing demands for water is to increase snowfall in mountainous areas through techniques of weather modification. On Elk Mountain, 40 miles west of Laramie, the University of Wyoming operates a water resources observatory. Here, scientists are conducting experiments to determine the effects of artificial cloud seeding on snowstorms. There is no need for increased snowfall on Elk Mountain itself. The site was selected because its 11,000-foot summit is frequently cloud-covered during winter months, enabling the scientists to study cloud processes directly.
Weather-wise, it looks to us, what's the cloud bases over there at this point in Cape?
Our cloud-based cloud tops still holding out at 9.3 and 14 respectively. The winds in the Teisaku Valley apparently have gone a little bit 280, 290 already, and I guess, as you know, Casper and Lender have shifted, so we might have a wind problem here as far as targeting goes, but cap cloud-wise we should be okay for the rest of the day.
Seeding agents and tracer chemicals released at a base station are carried into the cloud cap by the airflow across Elk Mountain. Aircraft from Wyoming and from the National Center for Atmospheric Research measure large airflow patterns over the Medicine Bow and Park ranges, as well as in the vicinity of Elk Mountain, and provide supporting meteorological data for the seeding studies.
44054, report a level at 12,000, please. Your radar contact 14 north of Cheyenne. Roger, we'll check level.
At the summit of Elk Mountain, a line of filtering devices collect samples of tracer particles. Zinc sulfide is generally used as a tracer because it is fluorescent and can be sensitively measured. By correlating the concentration of zinc sulfide on the ridge with the release rate at the base station, the scientists can tell how much of the seeding agent has actually reached the cloud. The principle behind cloud seeding is relatively simple. Just as a foreign particle caused supercooled drops to freeze in the laboratory, particles introduced into a supercooled cloud may also act as ice nuclei, turning millions of cloud droplets into minute ice crystals, which grow to become snowflakes. But of all the particles in the atmosphere, natural or artificial, only certain ones can cause freezing. And of those, each has a different threshold temperature at which it begins to work. A special nucleus counter measures the concentration of particles in the air, which can act as nuclei at various temperatures within a cloud. After water droplets have been cooled to a specific temperature, outside air is drawn over them. Attracted by a 5,000-volt electric field, particles in the air rush to the lower plate and collide with the droplets. At the moment of freezing, thermocouples beneath each droplet record the release of latent heat. The lid is open for demonstration only. Strangely, the number of snowflakes falling during a heavy storm often far exceeds the number of available nuclei. What accounts for this surplus of crystals? No one knows as yet. In some storms, cirrus clouds may play a role. Made up entirely of microscopic ice particles and forming at great altitudes, cirrus clouds are difficult to study. But cirrus-type crystals can be grown in the laboratory for analysis. At extremely low temperatures, the -40 or lower found at high altitudes, ice crystals will form spontaneously, without nuclei. Drifting downward, these crystals act as nuclei themselves, seeding the storm cloud below, or so the theory goes. But such inquiries into the nature of the cirrus crystal, or the problem of crystal multiplication, are still at an early stage. One of the more spectacular forms of atmospheric ice found on Elk Mountain is a feathery coating called rime. Driven by the wind, supercooled cloud droplets freeze on every exposed object. Rime is collected on the ridgetop to see how much seeding agent it contains from moisture in the cloud.
Pole number 5 had bag number 28 for the lower rod. Average wind 30, gusting to 50. Average wind speed 30 miles per hour, gusting to 50 miles per hour.
Other scientists study rime because it represents an important growth process in clouds. A snowflake falling through the supercooled liquid cloud will also accumulate rime. When it gathers so much rime that it is no longer recognizable, it is called graupel. Many summer downpours come from graupel, which melts on its way to Earth. Graupel also acts as an embryo or central core for the growth of hailstones. Hail falls only from giant thunderstorms, whose powerful updrafts can suspend the heavy balls of ice while they grow. Hailstorms are one of the most widely occurring of all natural disasters. While the toll of death and injury is small, dollar losses each year run into the hundreds of millions around the world. The ability to control these storms is still in the future. But in northeastern Colorado, a major effort is being conducted. The National Hail Research Experiment. Under the leadership of the National Center for Atmospheric Research, researchers from many organizations and disciplines have joined in the most comprehensive study of hail ever undertaken.
Yes? The storm at 04055.
Their purpose is twofold: to investigate the mechanisms of convective storms which produce hail, and to determine the feasibility of cloud seeding as a means of hail suppression.
5 Yankee, if you think that we need one more on this line.
7 Whiskey Papa, Cardi. 7 Whiskey Papa, Grover.
A lot of ice in this one, Kevin.
One key to the hail-forming conditions inside a storm is the record contained in the stones themselves.
Storm of 18 July.
Thin sections of hailstones examined under polarized light reveal layers of growth and crystal structure. These give clues to the moisture, temperature, and winds inside hailstorms. But our ability to decipher this coded storm history is still elementary. The destructive power of hail depends mainly upon size. It is not hard to imagine the deadliness of stones like this one, which fell in Coffeyville, Kansas. On the other hand, small stones may be more beneficial than rain, since the meltwater seeps into the soil rather than running off. Seeding to suppress hail works the same way as seeding to increase snowfall, by nucleating supercooled cloud droplets to form ice crystals. With a greater number of ice crystals competing for the remaining water in the cloud, no ice particle can grow as large. In theory, this will produce more but smaller hailstones that will melt before reaching the ground. But successful seeding is very complicated. To achieve results requires seeding in the right place, at the right time, with the right amount. Until now, much of our knowledge has come through trial and error. If ultimately hail suppression proves to be feasible, the current experiments will provide a more thorough scientific base for any future attempts. Whether we seek to control or merely to understand the power and grandeur of the storm, many of its secrets lie in the microcosm of its inner core, in the birth and growth of individual ice crystals.